So I want to just spend a few minutes first talking about how this course will be a little bit different now that we're not meeting at school. We'll be submitting all of your work online, and I've got a quiz posted. It's a take-home quiz. You could treat it like an assignment, like the same rules as a problem set. So it's okay to ask questions and refer to your notes if you want to. I didn't make it extra hard or anything. So you can find that if you go to Canvas, over here on the left side, on this menu on the left side. If you don't see that menu, by the way, like if you're on Canvas, you don't see that menu, just click on, like, I call this thing the hamburger at the top left, next to where the name of the course is, and it'll open that up, and you click on assignments. And then there's quiz 4, which is a take-home. You'll see a PDF that you can open. You could print it out if you want, or it's okay to just, look at the document and do the problems on other sheets of paper. You're going to be submitting all of these online, which means you need a way to scan. But you could do this if you have a scanner. That's great. If you don't, there are apps available on the phone on smartphones. So there's a link to this guidelines to submitting assignments online. It just takes you to this page that's in the top module here. There are apps like Cam Scanner and Adobe Scan. Those are the two that I've used successfully. There are others, I'm sure. So just pick one that works. And what it does is it just uses the camera on your phone to create a PDF. And what I'm hoping that will be the case, what I'm hoping for is that it runs it through a particular filter, so it actually looks like a scanner quality, document. So like here's an example, of what a good scan kind of looks like. There's like really good, let's see if it'll open it. There's really good contrast, right? And then sometimes it'll just look like a photo that's converted to PDF, and that's less useful to me. But however you can get it, I'll take it. But I'm hoping to get more submissions that look like the one on the left here versus the one on the right. Usually it's just a matter of telling it to use a different filter. And then you can submit on Canvas. So you go to assignments, and I'm in the instructor version here, the instructor view, but when you click on the quiz, in addition to seeing the document, there should be a button where you could say create a submission, and it'll let you upload your PDF. So that's how you'll be turning in your work. So I've got that quiz that's due Wednesday, so you got 2 days to do it. I didn't make it any longer than usual. You could sit down and do it like it's a regular quiz if you want, but it's okay to refer to notes and ask questions. I've also got problem set 3 posted, and that's due a week from Wednesday. We're finishing up this chapter today. So problem set 3 is posted, and then test 3, the test on this chapter is going to be a take-home. I will post an announcement, and I'll talk more about that when we have class again on Wednesday. But it'll be a take-home. There will be some rules about what you're allowed to refer to and what you're not allowed to refer to. I'll be pretty clear about what those are, and then we'll just kind of take it from there. Before we start on any new stuff, are there questions? Does anybody have questions they want to ask? Any questions on how this is going to go? Okay, so we're finishing up the Chapter 3 notes today, and I know that you don't already have the Chapter 4 notes handouts, but if you go to Canvas. Right at the top, it says course documents. And at the bottom, it just says 1520 lecture notes. So it's the lecture notes for this course. And if you open them, it's the lecture notes for the entire course. So we're in the middle of the applications. And when we start the next chapter, which we'll probably do on Wednesday, we'll be in chapter 4. So you could either print them out or you could just sort of use them. Give yourself a heads up. You could take notes on regular paper if you want, but if you wanted to print them out yourself, you can. They're available here. So that's my plan. That's sort of how I see this going forward. One more. Just gonna pause for a moment and see if there are any other questions. Just to see if there are any questions before we start the new stuff. Sorry, I'm responding to a student right now, so I'm not, this isn't social. Okay. All right, so hopefully we'll have another student joining us. If there aren't any other questions, feel free to enable your microphone. You can pause, stop me if I'm going too fast through something. It's okay. You can also use the chat window, but we can enable microphones for a reason. So if you have questions, please stop me. We're looking at these optimization problems or applied maximum minimum problems. And you know that the last bit of new material we did, we were doing curve sketching. And, with curve sketching, we're doing all this stuff to analyze a function, to understand its behavior. And in this section, we're really just zeroing in on one piece of what we did there. And that is just finding a maximum or a minimum and using it to solve certain word problems. So what happens when you see these word problems, what you'll get is they'll describe some scenario. They'll tell you some quantity that they either want to be maximized or minimized. And so you want to determine what we want to maximize or minimize. Sometimes it's helpful to kind of sketch out what's going on. Sometimes it's not. You want to make sure that you can draw an equation or write an equation for that quantity. And this part's important in terms of some other single variable. You want only one other variable involved, okay? Then you're going to find Q prime, which is, this means with respect to that one other variable that we used in the equation in step 3. So we're not differentiating with respect to time unless, of course, time happens to be that other variable. And, we're looking for a maximum or minimum, so that means we're finding critical values. We're going to set the derivative equal to 0 and solve, and then see if we found a max or a min. Like this part, people often forget this step. Sometimes there might only be one critical value, and we just assume it's the one we're looking for. And a lot of the time it is, but you want to check. You want to verify that it is, in fact, the maximum or the minimum. So check by either making a sign chart for the first derivative or check the concavity using the second derivative at that point. So we're going to do a few examples together. So in this example, a farmer plans to fence a rectangular pasture adjacent to a river. So she's using the river as one side of this pasture. And then she's got a total of 600 meters of fencing. We want to find the maximum possible area of the pasture. Now, so one thing that I'm just going to notice about this problem, and we're going to see this in pretty much all of these problems, is that they're telling us some quantity to maximize or minimize. But then there's also some constraint, right? In this case, it's that she only has 600 meters of fencing. Obviously, if there were no constraint, if you want to, there is no maximum. Just keep going, keep adding more and more fencing available, right? So she only has 600 meters of fencing, and that's what makes this an interesting problem. Is with a fixed amount of fencing, we could find the dimensions that will maximize the area that she can enclose. So we want to maximize the area. So I'm just going to write that down. Maximize, and then the area is what? Length times width, or x times y in this case. So I have my function. I've got the function that I want to maximize. I'm not ready to differentiate yet because it's not written in terms of a single variable. I've got two other variables, so we're not ready for the derivative. What we're going to do to get rid of one of those variables is use this constraint that she has 600 meters of fencing available. So this perimeter is 600 meters, or the three sides, rather, add up to 600 meters. So that's x plus 2y equals 600. I can use that relationship between x and y to eliminate one of the variables. The easiest way, I think, is just to eliminate, to figure out what x is as a function of y. So x is 600 minus 2y. And I'm going to take this and put it in right there. So now our area is 600 minus 2y times y. So there I've got the function written in terms of a single variable. We could at this point jump right into the derivative, but I want to make this as easy on myself as possible, so I'm going to distribute that factor of y. And now taking the derivative is easy because it's just a polynomial. So a prime, or dA dy if you prefer, is, somebody may have noticed I distributed the y, but I forgot to distribute it to the first term, so that should be a 600y. So 600 minus 4y. There's our first derivative. We want critical values. So the next thing we do is set a prime equal to 0. And if 600 minus 4y is equal to 0, that means 4y has to be 600. We divide by 4. And we get 150 meters. We only found one critical value. Hopefully, this is the one that actually does maximize, but we want to check. We want to make sure that at this critical value we confirm that we have either a maximum or, if it turns out this in fact gives us a minimum, maybe there is no max, right? So we're going to determine whether this is a max or a min. And we have two ways to do it. Really, you could just pick your favorite way. You can either make a sign chart for the first derivative or use the second derivative. And I usually just pick whichever one seems easiest given the scenario. So look at a prime here. A prime is 600 minus 4y. I'm going to just find the second derivative. A double prime is constant. It's negative 4. The second derivative is always negative, which means that A is always concave down. That means that at y equals 150, it has to look like this, right? Which means that y equals 150 gives a maximum. So I could find the other dimension now. If y is 150, then I could use this expression for x that we used at the beginning to figure out what our length x is. 600 minus 2 times 150. We get 300. And now the last step, which I kind of glossed over when I was looking at the procedure, but kind of important, I guess, right? Make sure you answer the question that was asked. They didn't say what are the dimensions that maximize the area. They said find the maximum area. So I'm not done yet. I mean, that's one step that's pretty simple, but we just want to make sure we go ahead and do it. Length times width is 150 meters times 300 meters. And that gives us 45,000 square meters. Okay, questions on that one? Okay. How's this? Is this working okay for everybody so far? Can I just get a check-in with each one, with each person, and?
Yeah, this is working.
Okay, great. Thanks, Carson. Other folks doing okay? Okay. All right. Okay, so let's do another one. We're going to find a point on the parabola y equals x squared that's nearest the point 6,3. What we're going to do, so the first step is figure out what we want to maximize or minimize. So we got this figure here, right? There's our parabola y equals x squared. Here's the point 6,3. And what they've done is they've just drawn a line from the point to some arbitrary point. I don't think there's anything special about where they drew it. Maybe it looks like that could be the nearest point, right? But what we're trying to do is minimize the distance between the point, the fixed point 6,3, and this other kind of variable point that all we know is it's somewhere on this parabola. So we figured out that we want to minimize the distance. And so we want to minimize the distance between 6,3 and x, let's see, xy, but we know that this point is on the parabola, so this point is really x comma x squared. So we want to minimize the distance. I think we have a way to do this, right? We have a distance formula. Let's see, I'll call this point my x2, y2, and I'll call this point my x1, y1. So we're minimizing this, which is the square root of x2 minus x1 squared plus y2 minus y1 squared, or x minus 6 squared plus x squared minus 3 squared. Now, I've got the distance written as written in terms of a single variable, right? So we could be ready to take the derivative. Again, I try to do a little bit of algebra if I can to make this process as easy as possible. You could take the derivative, right? The square root is the 1/2 power. You'd have a bunch of like chain rule stuff to worry about. What I'm going to do to make this a little easier on myself is just square both sides. I'm going to get rid of that. I'm still going to be able to get an expression for d prime, even if I start out with d squared on the left side. So if we square both sides, then we get d squared is equal to x minus 6 squared plus x squared minus 3 squared. I'm going to do some more algebra. I'm going to FOIL out these squares on the right side. So we have x squared minus 12x plus 36 plus x squared minus 6, oh whoops, that's x to the 4th minus 6x squared plus 9, and I'm going to just combine some like terms. X to the 4th minus 5x squared minus 12x plus 45. So there's d squared. Let's differentiate both sides with respect to x. So the right side is easy, right? It's just a polynomial. The left side is not too bad. We're gonna use, we're just gonna use like implicit differentiation. We're gonna differentiate d squared with respect to x. So we get 2d times d prime, or dd dx. And on the other side we have 4x cubed minus 10x minus 12. Let's solve this for d prime, right? That we're to get critical values, we need to have an expression for d prime. So I'm going to divide both sides by 2d. I'm going to cancel out the common factor of 2 on the right side. So that gives us 2x squared minus 5x, 2x cubed, rather, minus 5x minus 6 all divided by d. Now, it might seem like odd trying to solve this problem going forward when d prime is written in terms of two variables, not just one. But I'm going to tell you why that doesn't bother me. First of all, a derivative is 0 only when the numerator is. So I only really have to consider that 2x cubed minus 5x minus 6 being 0. Second, if it was important to have the bottom written as a function of x, I can do that, right? I have the ability. I could just take this as when we wrote down what d is up here in terms of x. I could just take that and plug it in, substitute it down here at the bottom. Oh, I just lost connection. Okay, sorry guys. I just dropped out for a minute. Hold on. Okay. All right. Sorry about that, everybody. I'm back. If you missed anything of where I was at, I was just explaining why it's okay that we have the derivative written in terms of a couple variables. So we want critical values. I want to know where d prime is equal to 0, so that's just when the numerator is. So I'm going to do, let's see. So if this is 0, that means that 2x cubed minus 5x minus 6 is equal to 0. Now we get, we're at a point right now. This is a little bit challenging to solve just because it's a cubic and there's no general cubic solution. There's not there's a quadratic formula, but there's not really a cubic formula. And we don't have other really convenient methods. So this is a scenario where I think it's a good idea to use our calculators, use some technology to help us solve this. Okay, so I am going to put in this that expression 2x cubed. Oops. 2x cubed minus 5x minus 6. Now I want to know where that's 0, so I'm going to look at the graph and then have it find the zeros for me. And an added bonus is when we graph it, we'll also be able to use the graph to confirm that we found a minimum or maximum. So I'm going to set just to the standard window from minus 10 to 10. Okay, so we could see we've got a 0 right there. I'm just looking to see where it crosses the x-axis. So on the calculator, I'm going to there's the trace button, and above it, it's in blue on my calculator, it says calc, so I'm going to do second calc. And the second option is 0, so I'm going to find the zeros of this function. It asked me for a left bound, and you can see I've got a blinking cursor. So I'm just moving it, as long as it's somewhere to the left of where I see it cross, that's fine. I'm going to hit enter. Now it wants a right bound. And the idea is when you make these bounds, you want there to be just one 0 in between the two bounds. There's only one 0 here anyway, but if there were multiple zeros, you want to just make sure that you've got a left bound and a right bound that encompass just one of the zeros. It asks for a guess. I always just hit enter. I don't put anything in. And there it is, x equals 2, y equals 0. So our calculator tells us that x equals 2 is the only critical value. Hopefully, this is in fact a minimum. And we can confirm that it's a minimum because look, on this graph, we could see that the derivative, first of all, I'm going to go back to the notes here. Here's what the derivative is, right? Is this expression here. This denominator, d, is always positive because that's a distance, right? That was the square root of the sum of the squares. This is always positive. So even though what we're graphing is not the whole derivative itself, it does, the signs of the derivative don't change, right? So the sign, like whether or not the derivative is positive or negative, is determined entirely by what's going on up here in the numerator. So when I graph the numerator, that graph is going to serve as basically a sign chart. Like, basically, if I were to use this graph, looking at this graph, I could make a sign chart for the first derivative that says it's negative, 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 all the way up until you get to 2 where it's 0, and then it's positive thereafter. So looking at the graph, I can see that d prime is going to look like this. And that's confirmation that, in fact, we've found a minimum. And the last thing we need to do to finish this problem is to find the coordinates of the point, right? Find the point on the parabola. We have the x-coordinate, so we want to find the y-coordinate. Which is pretty easy, right? It's on the parabola y equals x squared, so that means y is equal to 4, and the point 2, 4 is the point on the parabola. That is nearest the point 6, 3. Great. How's that? Are there questions on how we solved that problem? Okay. All right. One more to go here. We want to find the dimensions of a 700 kiloliter cylindrical oil tank that has the smallest surface area. Okay. So I'm going to go ahead and assume, I mean, it's drawn in a particular way. I don't really understand. This is an oil tank, right? I'm going to assume that it's closed at the top. It doesn't really make sense that there would be an oil tank that's just sitting open. So I'm assuming that this cylindrical oil tank has a top, which contributes to the surface area. The other thing that we want to keep in mind is that a kiloliter is 1 cubic meter. So we know that the volume of this oil tank is fixed. The volume of the cylinder is fixed at 700 cubic meters. And we want to minimize the surface area. So we know the volume is 700 cubic meters. We want to minimize the surface area. So the volume, so we might have to look up some geometry formulas if we don't have these memorized, but for a cylinder, the volume is pi r squared h. So we know that pi r squared h is equal to 700 cubic meters. That's just a relationship between the radius and the height. What we need now, we want to minimize the surface area, so we need that function. And, ultimately, right, we want that function in terms of a single variable, but we're probably going to have both radius and height involved at first. So for the surface area, for starters, we have both the top and the bottom, and both of those are a circle of radius r. So that's 2 times pi r squared, right? That's for the top and the bottom. And now we need the area all the way around. So, and you could look this up online, but the lateral surface area, that's what we call it, is given by, if this is our cylinder, so it's open, right, and I just want the surface area around. I imagine that I could cut it up the side and unroll it, and when I do that, I see that, oh, that doesn't like the background very well. I see that it's really just a rectangle, and one dimension is the height, and the other dimension is like the circumference of the base. So that gives us an area, this what we call the lateral surface area of 2 pi r, there's the circumference, times the height. So there's our surface area of this cylinder. We've got it written in terms of 2 variables instead of 1, so we need to pick a variable to eliminate. Now, really, it's up to you. Theoretically, either variable will work. I'm going to pick eliminating h because it only shows up once, so I have to make one substitution, and I feel like that'll be easier. So I'm going to go over here to the left where we're working with the volume and just solve for h. I'm going to take this expression, substitute it in up there. Now I have not taken the derivative yet, right? So this is still just the area. I could do some simplifying, cancel the pi, cancel 1 factor of r. 2 times 700 is 1400. So let's see, I've got 2 pi r squared plus, I've got 1400 over r, and because I'm going to be getting ready to take the derivative, I'm going to write this as 1400 r to the negative 1 power. All right, so there's, power rule friendly form. Let's take the derivative. So a prime is 4 pi r minus 1400 r to the negative 2. So the negative exponents were super useful in making it easier to take the derivative. We want to find the critical values. We want to set the derivative equal to 0. So I'm going to go back to fractions. That's going to make it easier to solve. So setting a prime equal to 0 means that 4 pi r minus 1400 over r squared is equal to 0. There's more than one way we could choose to solve this. I'm going to go ahead and throw this fraction on the other side here. So I'm just going to add 1400 over r squared to both sides. I'm going to multiply both sides by r squared. Pi r cubed is 1400, and divide both sides by 4 pi. Oh, I said r cubed and then I wrote r squared again. Okay, so now r cubed is, let's see, 1400 over 4 is 350, so 350 over pi. And we're going to take the cube root. So if we take the cube root, we find that r is the cube root of 350 divided by pi. We can approximate that. Putting the whole fraction in parentheses first and then raising it to the 1/3 power to take the cube root. So about 4.81 meters. Now we don't know yet. So we found one, there's only one cube root. With square roots there's a positive or a negative, but cube roots is just one real cube root of a number. So there's one critical value. Hopefully that minimizes the surface area and doesn't maximize. But we got to verify that. So let's verify that this radius gives a minimum. And so our first derivative is 4 pi r minus 1400 r to the minus 2. And to verify that we have a minimum, I'm going to find the second derivative. If it is a minimum, I want it to be what? Concave up, right? So hopefully, we'll find the second derivative and then plug in 4.81, and if it's positive, that means it's concave up, and we will have found a minimum. So we get 4 pi plus 2800 r to the minus 3, or 4 pi plus 2800 over r cubed. If we plug in 4.81, I don't think I need a calculator to do this, or I need a calculator to actually find the value, but I don't need a calculator for the analysis, because this is very clearly going to be positive. 4 pi is positive, and I'm adding another positive. 2800 divided by 4.81 cubed has to be positive. So this is positive, which means that we found a minimum. And the last bit of this problem is making sure that we've answered the question that was asked. So they asked for the dimensions, I think. Find the dimensions, plural. So we found the radius. That means we also need to find the height. But look, we've already got height in terms of radius here. So I'm just going to take that, use it to find the height of the cylinder. So pi r cubed, so pi r squared rather, so that would be 350 over pi to the 2/3, right? So it's the cube root and I'm squaring it. So the cube root means it's a 3 in the denominator and I'm squaring it, so it's a 2 in the numerator of the exponent, and we can get an approximation. Or you can put in 4.81 as an approximation, throw that in your calculator. Divided by, now I got to put the whole denominator in parentheses, otherwise it'll think I want to multiply by the r squared. So pi times closing out the parentheses in the denominator, 9.62 meters. So there's our radius, there's our height, and these are the dimensions that minimize the surface area. How's that? Any questions about how we solved that, how we set it up? Okay. So that's the end of this section. I'm going to go back and just for folks who missed it, we're obviously now submitting all of our work online. There is a take-home quiz posted. It's the same rules as the problem set, so you can refer to your notes, you can ask questions. It's due Wednesday, so that's in 2 days. I wanted to get us working on having something to submit online, so we have practice making sure that we're all ready to do that and can do it successfully. In order to create a PDF, I would recommend getting one of these apps, either Adobe Scan or Cam Scanner. If you already have an app that does the same thing that you like, please by all means use it. But it'll create a PDF. There's a page here in Canvas, Guidelines for Submitting Assignments Online. Make sure that you write clearly. I need to be able to read what you're writing. And I work really hard. I want to give you as much credit as I can for the good work that you're doing, but that means I have to be able to read it. So don't make them too cramped. If you fit all 4 problems on one page, that's probably a bad sign. You should probably be using at least 2 pages when you work out these problems. Sometimes, folks like to put each problem on its own page. That's great. So you could either print out the quiz if you have a printer, or you could just do the problems, just look at the quiz and do the problems on your own paper. That's fine, but you're going to create a PDF. And you can, when you have that, when you use the Adobe Scan or Cam Scanner to create a PDF, you can email it to yourself or something so that you can upload it to Canvas, or maybe it works well from right within the Canvas app on your phone. When you click on this, there's the quiz right there as a PDF, and then there will be as a student view, you'll see a button that says create a submission. You want to upload that no later than midnight on Wednesday, and then I'm going to grade them on Thursday. Also, just as a reminder, I've just posted the problem set. We just finished this chapter, so there's a problem set that's due a week from Wednesday. That's on the 1st. And on Wednesday, I'll talk more about getting ready for our next test, which will be a take-home test. There will be some rules, some what I think of are reasonable rules for how that'll work. But again, doing all of this depends on us being able to create a PDF from our handwritten work and submitting it online. Does anybody have questions about just the logistics for how to make this, making this work from home? Okay. Okay. So what I'll do then is I guess I'll call it for the day. We got through all the material we wanted to get through. On Wednesday, I'm going to start by answering your questions. Take a look at the quiz, take a look at the problem set, and then we'll get started on Chapter 4. So remember, Chapter 4 is available. If you want, if you have a printer and you want to print it out, you can. If you just want to take notes on regular paper, that's also okay, and I'll be posting my notes as usual to Canvas. If you have questions or if you have any trouble like creating a submission, I want you to email might be best. My cell reception is spotty where I am at right now. If you have like an iPhone and it gets sent via iMessage, I'll get it because I can get it via Wi-Fi, but I don't have a lot of cell service. So it might be best, email might be best if you have any trouble. If you encounter any trouble trying to create a submission or scan your work. Okay. All right. Thanks, everybody. I'll let you go, and we'll connect again on Wednesday morning.